Here we're going to look at another type of polar graph, and we're going to graph it using a different approach than how we graph the rose petals. The rose petals, I had us graph the rectangular form of this equation here, and then sort of map it onto the polar one. But here I'm going to do something a little more straightforward, which is just evaluate these directly, and I'm going to use our calculator for now, just so we can kind of streamline the whole evaluating process and get some answers here. So now a couple of these we can do in our head, right? When theta is 0, then r equals 2 plus 2 times cosine of 0, and the cosine of 0 is 1, so it's 2 plus 2 times 1, which is 4. Pi over 2 one we can do as well, because 2 plus 2 times the cosine of pi over 2 is 2 plus 2 times 0, since the cosine of pi over 2 is 0. So that's 2 plus 0, which is 2. The cosine of pi is negative 1, so 2 plus 2 times the cosine of pi is 2 plus 2 times negative 1, which is 0. And then 3 pi over 2 is the same as pi over 2 because cosine of 3 pi over 2 is 0, so it's 2 plus 2 times 0. And since 0 and 2 pi are the same, then those values are going to be the same. Okay, and now the others I'm going to just punch into the calculator, and I trust you can do that, but the first one would just be 2 plus 2 times cosine of pi divided by 4, which is 3.414. Okay, and when I punch in same thing, but 2 plus 2 times the cosine of 3 pi over 4, I get 0.586. And with 5 pi over 4, 0.586. And with 7 pi over 4, I get 3.414. Okay. So now let's just plot these points and look at what we see. So when theta is 0, I'm rotating 0, and I walk out 4. So there's my first point. When theta is pi over 4, I walk out 3.414. And pi over 4 is 45 degrees, so I walk out a little farther than 3. And when theta is pi over 2, I walk out 2, so I'm facing pi over 2 and walk out 2. When theta is 3 pi over 4, 135 degrees, I walk out 0.586, so about, a little more than a half, which it's tough to do here, so this point can suffice. When I rotated pi, I walk out 0, so now I'm back at the origin. When I rotate 5 pi over 4, 225 degrees, again I walk out 0.586. 3 pi over 2, I walk out 2 again. So I rotated 3 pi over 2, I walk out 2. 7 pi over 4, I walk out a little more than 3. And then at 2 pi, I'm back to 4. So if we trace this path, you have this nice heart-looking graph, and that's why they often are called cardioids. Cardioids, right? Cardioids, cardiac, comes from the, I don't know, Latin or something for heart, but they look like hearts, so that's why it looks like that. I think the mathematical term for them is this, lemmason or lemacon. To be honest, I don't know. I don't find the pronunciation of that too interesting. I call them cardioids, but they're also called limesons. I don't know. But the more important thing is that these are always going to be the result of a polar equation that has this form. Okay, anything of that form tends to look like a cardioid or a limason. I'm gonna have to go Google that or look it up because textbooks can't talk to you, so I didn't know how to pronounce it. Anyway, this is just our first example of another type of graph as opposed to our roses. So we've got roses and hearts, which, too bad we couldn't have done this right by Valentine's Day. It would have been perfect. But there's our first example of how to plot those, how to graph those.